Hey everyone, my name is Bhaskaram, and in this video we are going to talk about thermal noise in a resistor. So it's also sometimes called the Johnson-Nyquist noise, but it's just different names for the same thing really. So thermal noise is essentially generated due to the random thermal motion of charge carriers inside a conductor. So that sounds like a mouthful, but what I really mean is that if you have a conductor and there's some current flowing through it, then the electrons are not going to flow in a straight line through the conductor. So, for example, not something like the path of the electron shown in the red. It would look, in practice, it would look something more like the electron in the blue, where it's just hitting around, it's just bouncing off in a random motion through the conductor. And so you can imagine that if you're, measuring current through a cross section of this conductor, then what you're going to get is, at a certain time instant, there might be fewer electrons than expected. At some other time instant, there will be more than expected electrons. And so if you're plotting the current versus time, you would see something like this, where the current is noisy because because of this random motion of electrons through the conductor, basically. And so this is called thermal noise because it has a dependency on temperature. This random motion of electrons, it becomes more vigorous if the temperature is increased, or if, in other words, if the conductor is placed at a hot temperature. This random motion would be more vigorous, and which would mean that the noise current would be higher if the temperature is higher, which is why it's called the thermal noise. And it's also actually one of the reasons why we want to sometimes have electronics at a low temperature, because we want to reduce thermal noise in our electronics as much as possible, so that we can receive like very small signals. This is sometimes common in electronics for scientific instruments, or you might have seen pictures of a quantum computer where they have all of the quantum chip inside a dilution refrigerator, which is basically trying to keep all of the electronics as cool as possible. And essentially the reason is like, one of the reasons is that you just want to reduce the thermal noise in your resistors, in any conductors really, as much as possible by cooling down the temperature. Okay, thermal noise is also white in nature. So what that means is, if you're plotting the thermal noise power spectral density, then it would be flat for all the frequencies. And we'll talk later that this is actually not the case, but I'll just leave it at that at this point. All right, so resistors exhibit thermal noise, and so if you want to model thermal noise in a resistor, you could replace a noisy resistor with a model like this, where you have a resistor of an equivalent resistance R, but it's noiseless, but it is in series with this noise voltage source. And so that models the thermal, this voltage source models the thermal noise in a resistor. And so what we would find out later on is that the average noise voltage in a resistor is 4 kdBr. Or alternatively, you can also model a resistor. So again, sorry, uh, the resistor here is noiseless, and you can model a noisy resistor, but in a configuration like this, where you have a noiseless resistor in parallel with a current source, a noise current source that models the thermal noise of a resistor. So both models are fine and they're possible. You can use them while doing your noise analysis. And what we would find out later on in through derivations in this video is that the average noise current in a resistor would be 4 kdB over R. And the bar here, the bar here, and the bar here basically just indicates an average. Also, the voltage noise spectral density, or NSD, is basically just the average noise voltage divided by the bandwidth. So that's 4 kdR. And again, same thing for the current. For the current NSD, it would be the average noise current divided by the bandwidth, which is 4 kd over R. And these are basically, if you're taking away anything from this video, it would basically be these expressions so that you can use them in your noise analysis. But later on in this video, I'm also going to do a quick derivation of how I got these expressions. All right, so a few notes about thermal noise in resistors. One thing is that the first thing is that thermal noise is only associated with real resistors. So, as an example, if you've studied BJTs, you would have seen that we model BJTs and there's this resistance called R pi. Uh, that resistance is a fictitious resistance. It's not something real inside a BJT. And so, uh, would would this R pi resistance generate thermal noise? No, because it's not a real resistance, right? It's a fictitious resistor that we have used for modeling purposes. Okay, another example would be, you can make resistors out with inductors and capacitors, but those are not real resistors either. And so, do those resistors exhibit thermal noise? No, right? And so, that was the first thing. And then the second thing I wanted to note is thermal noise. We previously said that the thermal noise is white in nature, but as it turns out that we can't have a truly white noise, and that's because the average power, which is basically the area under the curve of this PSD graph here, um, that would be infinite. The average power would be infinite if the noise is truly white for all the frequencies until like infinite frequency, right? And so that's not possible. And so what we see in practice is indeed the white noise falls off in the terahertz range. Or sorry, the thermal noise falls off in the terahertz range, and so it's not truly white. So that's just something to be aware of. But if you're not operating in the terahertz range, or if you're operating at somewhat lower frequencies, then for all intents and purposes, you can assume that thermal noise in a resistor is white in nature. All right. And then a third note, just in general, is the definition of PSD, or the definition of power spectral density here. So there's two different ways to define PSD. One of them is one-sided PSD, and the other one is two-sided PSD. And essentially, the only difference really is that for one-sided PSD, you're only considering the positive frequencies, but some people like to, consider two-sided PSD. So in that case, you're considering both the positive and the negative frequencies. Now, the only reason I mention this is that the average power is, in one-sided PSD, it's the integral of the PSD for a certain frequency range, let's say from F1 to F2. So that's for one-sided, but for two-sided PSD, it's the same integral multiplied by 2. So if you're doing your noise analysis and you're off by a factor of 2, or in your equations there's a factor of 2 popping out, it's worth checking out if what is the definition of PSD that's being used, if it's one-sided or two-sided, and if there's any misunderstanding between the two while you were doing your derivation. So that's the only thing I wanted to mention related to this one-sided versus two-sided PSD. Both are equivalent, and I mean both are equally valid. It's not like one is right and the other one is wrong. It's just two different representations that are used, and so you just want to be aware which one you're using, and so that you're arriving at the right expressions. All right, so that was pretty much it for the content for thermal noise. But as I said previously, we had these expressions for average noise voltage in a resistor and average noise current in a resistor, and then voltage NSD, current NSD. So these expressions have a derivation, and so that's what I'm going to talk about now. So imagine you have a circuit like this where you have a noisy resistor. Oops, sorry. You have a noisy resistor, and you're connecting it to a power meter. And that power meter has impedance matching. So what that means is the internal resistance of this power meter is equals to R, which is the same as this resistance R here. So so that's all I mean by impedance matching. And so what we will find is that in this kind of circuit, the average power which will be read by the power meter, would be kdB. Okay, and then another thing I want to mention is for thermal noise, what we find out is that the PSD is 4 kT. And it's white in nature. Again, we're assuming it to be white. And so let's think about the average power. So the average power is essentially an integral from F1 to F2, which could be any two frequencies, and integral of PSD, um, right? And essentially it's just area under the curve of this graph here, right? So if this is the PSD graph, then it's just the area under the curve for a certain frequency. So let's say from here I have highlighted from 0 to the bandwidth B. And so this integral would be something like this, where the average power is from an integral from 0 to B of the PSD curve. And since this PSD is white in nature, you're looking at a constant line, right? So this is basically now just an area of the rectangle, which is highlighted in pink, right? So this integral would basically be just an area of a rectangle, which is power spectral density multiplied by the bandwidth, right? And so then we can find out that the average power is equal to 4 kTB. All right. Now let's look at the average noise voltage of a resistor. So the average power is also equal to V squared over R, right? And so we previously found out that P average is 4 kTB. We can say that this V squared over R term is equal to 4 kTB, and that's how we get the average, or the average noise current, which is 4 kTB R. And so that's a major takeaway. And this is essentially, again, if you're modeling the resistor with a noisy voltage source, or a voltage source that is modeling the thermal noise of a resistor. And the voltage noise spectral density would look something like this, where it has where it's of value 4 kTR. And so, by the way, it's the voltage noise density is the same as this term here divided by bandwidth. Okay. All right. So now let's look at the average noise current of a resistor. So again, now instead of voltage noise source, we're now modeling the resistor, a noisy resistor with a current noise source. So previously we found out that voltage NSD is 4 kTR, which is right here, right? So then we can say that we have a system where the input is the voltage NSD and the output is current NSD, and the transfer function of a system like this, since we have current at the output and voltage at the input, the transfer function is just 1 over R. And so then we can write that the current NSD is equal to the transfer function squared multiplied by the voltage NSD. So then that expression would just, so then when you do a little bit of algebra, you will find out that the average noise current is 4 kdB over R, which is the same result as what we found, or what I mentioned over here. So here, 4 kdB over R. So that's how we get these expressions, basically. And that is pretty much it for thermal noise of resistors. And next we will be discussing the thermal drain noise in a MOSFET, and gate noise in a MOSFET, and other kinds of noises. So stay tuned, and I'll see you in the next one. Cheers.